Um, Thank you, and thanks everyone for coming, and thanks for the invitation. My name is Hao Chen, and I will talk about the Dehn twist on a sum of two homology tori. So the goal of today is to show that the S1 equivariant family powerful time invariant detects non-trivial elements in the mapping class group for non-simply connected manifold. So of course, there are many previous results on the detections of powerful time invariant. For example, Hammer and Morfkai used non-equivariant family powerful time invariant to show that the Dehn twist along the 3-sphere in the neck of a connected sum of K3 surface is not smoothly isotopic to the identity. And later, Jianfeng Lin used the S1 equivariant family powerful time invariant to show that the above Dehn twist is still not smoothly isotopic to the identity after the stabilization by S2 cross S2. These examples are for simply connected manifolds. Now we have a result for non-simply connected manifold. So we use a refinement of the S1 equivariant family powerful time invariant to show that if X1 and X2 are homology 4 tori with odd determinants, then the Dehn twist along the 3-sphere in the neck of X1 connect sum X2 is not smoothly isotopic to the identity. So I will take the whole talk to explain the notations and the definitions here. But before that, I have to mention that the non-equivariant version of family powerful time invariant doesn't work. For these two cases, but the reasons are different. So in Jianfeng's case, it's because S2 cross S2 will contribute to an element in a stable homotopic group of sphere which has incorrect dimension. And in our case, it's because the index bundle of this manifold has a non-trivial structure. So I have to use the S1 equivariant invariant. Okay, before we start, I have to state some notations. So SMR and SMH are the one-point compactification of n-dimensional Euclidean space and m-dimensional quaternion space. And for pointed space X and Y, we define the smudge product of X and Y to be the following manifold, to be the following CW complex. We first take the product of X and Y, and then we collapse a copy of X and a copy of Y. And for space X, X lower plus is X union a base point star, and it's a pointed space. And we denote the suspension of X by sigma X, and is S1 smudge X. We will denote the homotopic class of stable maps from X to Y by brace XY, and is defined by the limit of bracket suspension X, suspension Y. So, for example, high-N SM would be defined by brace SM SM, and people also use high-N stable to denote the nth stable homotopic group of sphere. So it's Sn plus M Sm. So for example, pi4 S3 is ZMO2 and is generated by the Hopf element eta. So I will draw a graph of eta. So here we regard eta as an element in S3, S2. And S3 is the three-dimensional Euclidean space plus a point at infinity. And we take a Hopf link in this space, and we send this blue circle to the North Pole, and we send this red circle to the South Pole. And each disk that is mounted by this red circle is sent to S2 by collapsing its boundary. But if we take a framing of this North Pole, then the pre-image of this point is a non-trivial framing from this circle. So by the Thom-Pontryagin theorem, the nth stable homotopy group of sphere is isomorphic to the nth framed cobordism class. So this is an example of this correspondence. And we also denote the Lie-framed circle by eta. Okay, the last notation is the Thom space. So if F is a bundle, then we denote its Thom space by TF. So for example, if we have a rank 1 bundle over a one-dimensional torus, which is a circle, then if F is orientable, then TF would be something looks like this one. So we take a sphere and we collapse 2 points on the sphere. And if F is non-orientable, then its Thom space would be RP2. So notice that we have the Thom isomorphism. So each cell in the base space would contribute to a cell in the Thom space. And the dimension is the original dimension plus the dimension of the rank of the bundle. So we will use this property later. Now we can discuss the definition of the Bauer-Fulton invariant. So we will use the following Seiberg-Witten map. So it's a map from the space of connections direct sum the space of positive spinors, mod out the best gauge group to the space to omega 0 direct sum the space of self-dual two forms direct sum the space of negative spinor. And we also mod out the best gauge group in the target. So the best gauge group is identity at a specific point. And the Seiberg-Witten map has two inputs, a connection and a spinor. And it has three outputs. So the first one is D star A minus A0, where A0 is a reference connection. And the second output is the curvature of A plus the quadratic term of phi. The last output would be the twisted Dirac operator, dA phi. So roughly speaking, we can split it into two pieces. So the first one is the map from the positive spinors to the negative spinors. And the second piece is the map from omega 1 to omega plus. And the co-kernel of this map would be the harmonic self-dual two forms. And we also have a map from the kernel of gamma S plus to the co-kernel here. So this is the quadratic term in the Cyber-Witten map. And the idea of Borel and Fruta is to take a finite dimensional approximation of the Cyber-Witten map, which means we can take a large enough subspace which contains the co-kernel, and we call it V minus. And we consider its pre-image, and we call it V plus. Similarly, we take finite dimensional subspace U minus here and its pre-image U plus. And the theorem of Borel and Fruta says for a simply connected smooth form manifold X and a spin structure S on that, the Cyber-Witten map defines a stable map from the one-point compactification of V plus direct sum U plus to the one-point compactification of V minus direct sum U minus. And we denote this element, we denote this map by BFXS. If X is not simply connected, we have a non-trivial edge up one. Then after we model out the best gauge group, this space would become a Picard torus. So in that case, the Borel-Fruta invariant would be an element in a homotopy class of stable maps from the time space of the index bundle to SNH plus B plus R, where the index bundle F is a rank M H bundle over the Picard torus of X. And M minus N is negative signature of X over 16. So the value of M and M actually depend on the structure of the index bundle. So as an example, we can take a look at the Borel-Fruta invariant of K3 surface. So it's an element in the homotopy class of stable maps from SH to S3R because B plus of K3 is 3. So in the picture, we will use this line to denote H and this line to denote 3R. So a theorem of Morgan and Szabo says Borel-Fruta invariant of K3 surface with its unique spin structure is the Lie frame circle eta. So I will sketch the proof. So so Morgan and Szabo proves that the Cyber-Witten invariant for the K3 surface is odd. So if we take a generic point in the target, which means we take a generic perturbation, then the pre-image would contain odd number of circles. And actually they correspond to pi theta phi. And by the property of the Cyber-Witten map, it's S1 equivariant. So if we take a framing here, then the pre-image is a Lie frame circle. So recall that if we have odd number of circles, then it's just eta because it's in the two torsion group. Now we can take a look at another example. So we let X be a homology torus and define the determinant of X be the valuation of alpha 1, alpha 2, alpha 3, alpha 4 on the fundamental class of X, where alpha 1, alpha 2, alpha 3, and alpha 4 is the basis of H alpha 1 of X. Then a theorem of Ruberman-Storley says the second Chern class of the index bundle of this homology torus is equal to the determinant, and the other Chern class vanish. So in a picture, we have a non-trivial index bundle in the domain with fiber H. And the base space is the Picard torus of X, which is a standard full torus. And since this bundle F is a rank 4 bundle, so the dual of C2F is a zero-dimensional manifold. So we use these blue points to denote the dual of C2F. Now we can regard the bundle F as a trivial bundle outside this dual of C2F. Then Danny and his student Sasho, they defined a perturbation of the Seiberg-Witten map. And it says the fiber here is sent to H in the target by the identity. And around these blue points, the fiber is twisted. And the image of this fiber is also twisted. And the fiber over these blue points are sent to 3R by the element eta. So as a corollary, we have that if the determinant of X is odd, then the ball full-time invariant of X with any spin structure is non-trivial. Okay, so I will sketch your proof. So we have a table of the cells in the domain TF. So recall that TF is a H bundle over the standard 4 torus. So I have 0 cell, 1 cell, up to 8 cells. And for the cells in the target, we have only 2 cells. The 0 cell and the 7 cell. And by a cofiber sequence, we can actually ignore these low-dimensional cells of the domain. And we only need to consider 6 cell, 7 cell, and 8 cell. And by the CW structure of the base space, which is a torus, we know that the attachment maps of adjacent cells are stably trivial. So this is the same for the COM space. So we have trivial attachment map. Now we can consider the attachment map from the 8 cell to those 6 cells. It might be eta. But we can compute the structure of the index bundle. We know that the W2 of F is 0. Then by the Cartan formula and the basic the basic definition of the Stirner square, we have SQ2 of the dual of any 6 cell in TF is 0. So the attached map from the 8th cell to any 6 cell in TF is not eta. So actually, we don't have eta here. Hence, in the stable homotopy category, we can regard TF as a wedge sum of spheres because all attached maps are stably trivial. So the stable cohomotopy group of TF would be a direct sum of homotopy groups of spheres. And if we look at this picture, then it indicates that if we take a generic point in a target, then the pre-image of it would be contained in a fiber. So this means that the Ball-Fruita invariant is eta in the homotopy class of top cells. So this proves that the Ball-Fruita invariant is non-trivial. Any question? Okay, now we can consider the family Ball-Fruita invariant. So we'll assume that we have a smooth family of X over the base space B, which is a one-dimensional space, and we denote this family by EX. Now we define the family spin structure on EX by the following. So let S be a family spin structure on EX, which is a double cover of the vertical frame bundle of EX that restricts to the standard double cover of spin 4 to SO4 on each fiber. And we call the pair EXS a spin family. So for example, we have two families spin structure associated to a spin structure S on X for the product family. So the first one is the product spin family S tilde, and the second one is the twisted spin family S tilde tau. So this is because if we take the identity in SO4, then it has two leaves to spin 4. One is identity, and the second one is the deck transformation tau. So the product spin family is just the mapping torus of the identity on X and the identity on the spin structure. And the twisted spin family is the mapping torus of the identity on X and the deck transformation tau on the spin structure S. Now we assume that the action of pi 1b on h upper 1x and h upper 2x given by the holonomy of the bundle ex is trivial. Under this assumption, we can define a stable map from the product B cross TF to the target SNH plus B plus R, and we call this map mu. So here F is also the index bundle. So it's a rank M H bundle over the picotors, and M minus N is M minus N depends on the signature of X. So Jianfeng Lin defined a family Ball-Fruita invariant that can simplify the structure of the domain, which would make the computation easier. So in his definition, the Ball-Fruita invariant, the family Ball-Fruita invariant, is a composition of the following maps. So first we take SR smash common space of F. Then we have a projection maps from this space to SR plus a base point smash TF. So this is actually, we first take a product and then we collapse a copy of SR. So here, infinity is the point, the infinity point of the time space. Now, apparently, we have a projection from SR cross TF to this space. And in the previous proposition, we have a map from the product to the target SNH plus V plus R. So now, in the original definition of Ball-Fruita invariant, we know that the point at infinity would send to the point at infinity. So we have a lift of such mu, and we call it mu tilde. So the family Ball-Fruita invariant is the composition of these two maps. So a theorem of Kramer-Morfka shows that if X is simply connected and S is the spin structure of X, then the family Ball-Fruita invariant of the twisted spin family would be eta times the original Ball-Fruita invariant if the signature of X is 16 mod 32. And otherwise it will be 0. So they prove this by studying the stable framing of the quaternion bundle, which I will explain later. And as a corollary, it shows that the family Ball-Fruita invariant of the connected sum of the twisted spin family of K3 surface and the product family of the K3 surface is eta q, and it's non-zero. So notice that this connected sum is just a mapping torus of the Dehn twist. So this proves that the Dehn twist is not smoothly isotopic to the identity. For the non-simply connected manifold, we have similar result as the first one. So if X is a homology 4 torus with odd determinant, then the family Ball-Fruita invariant of the twisted spin family is non-zero. So I will draw a graph to explain the situation in Kramer-Morfka's paper. So we have, if signature of X is 16 mod 32, then we must have one more edge in the domain and it will be mapped to some copies of R in the target. If we take a generic point here, then the pre-image would be the original Ball-Futa invariant. Now, if we take a family over S1, and the trajectory of this pre-image would be the different circle eta. So the family invariant would be eta times the original invariant. So in our case, we don't have such condition on the signature because for the homology torus, the signature is 0, but we have a non-trivial index bundle. So in our case, this one is replaced by the index bundle F. With fiber edge. And we have shown that this fiber must be mapped to some copies of R in the target. So the trajectory of the pre-image will also be a different circle. So this gives the result. However, we don't have such good condition and such good result for the homology torus because the structure of the index bundle is non-trivial. So we have the following theorem. If x1 and x2 are two homology torus, then the family Ball-Futa invariant of the connected sum of the twisted spring family and the product spring family is 0. So I will sketch the proof. So we compute the structure of the index bundle. So C2F of this bundle is determinant of X1 times the volume form of the Picard torus of X1 plus the determinant of X2 times the volume form of the Picard torus of X2. So this means that the attachment map from the top cell of TF to some 9 cells in TF is the hop element nu. So we also have a table. So the dimension of cells in the domain SR smash TF, we have a lot of low-dimensional cells, but the essential attachment map is the one from the 13 cell to the 9 cell, and it will be the hop element nu. But in the target, we only have 0 cell and 10 cell. So by the Atiyah-Hazelbrook special sequence, the map from the 13 cell here to the 10 cell must be trivial. So I will explain this phenomenon by a low-dimensional analog. So suppose we have S3 and CP2, and we consider the homotopy class of stable maps from S3 to CP2. The dimension of cells in S3 is 0 and 3. Dimension of cells in CP2 would be 0, 2, and 4. And the attachment map from the 4 cell to the 2 cell is the hop element eta. And if we want to have a non-trivial map from S3 to CP2, then the only possibility is the map from the 3 cell to the 2 cell, and it will be the hopeful element eta. But if we have that, then we will have a homotopy by this 4 cell, which can deform the image of S3 to a point. So this means that we cannot have a non-trivial stable map from S3 to CP2. So to solve this issue, we can consider the equivariant version. So recall that the Ball-Fruta, recall that the Seibel-Witten map is pin2 equivariant, but we only consider the S1 equivariant. We only consider the S1 action. So suppose we have an S1 action on S3 by the Hopf figuration, and S1x on CP2 trivially. Then by the equivariant Hopf theorem, this equivariant homotopy class is isomorphic to a non-equivariant homotopy class, because the action of S1 on S3 is free away from the base point. So we have such isomorphism. And the domain of this non-equivariant homotopy class is S3, and we model out the S1 action. So we know that if we model out the S1 action, then it will be a two-sphere. Now, this homotopy class of stable maps is non-trivial. So yeah, so to solve this issue, we have to consider the equivariant version of family Ball-Fruta invariant. However, we don't have such condition. So we have to consider refinement of the equivariant Ball-Fruta invariant. We define the quotient equivariant Ball-Fruta invariant by the composition of the following maps. So BF, family Ball-Fruta invariant. For a spin family EXS, would have domain SR smash TF or Picard torus of X. So here we regard the Picard torus as a zero section of F. And we also regard it as a subspace of TF. Then we will have a projection from SR smash TF to this quotient space. And the original S1 equivariant so this is a family Ball-Fruta. Would have domain SR smash TF and target SN H plus B plus R as usual. Now notice that the zero section of F consists of flat connections and a zero spinner. So they are always mapped to zero in the target by the definition of separator map. So we have a lift of the original family Bauer-Fruta invariant. Okay. If we consider this quotient invariant, then we see that the domain of this invariant is a quotient space of the original domain, and S1 action on this domain can be made to be free away from the base point. So we can apply the equivalent Hopf theorem and simplify to a non-equivalent stable homotopy groups and compute the invariant. So we get the following theorem. If the determinant of x1 and the determinant of x2 are odd, then the family Bauer-Fruta invariant is trivial, but the S1 equivalent quotient invariant for the product family connected sum, the twisted spin family is non-zero. So this connected sum is actually a mapping torus of the Dehn twist of x1 connected sum x2. So as a corollary, we have that if x1 and x2 are homology for tori with odd determinants, then the Dehn twist along the three sphere in the neck of x1 connected sum x2 is not smoothly isotopic to the identity. Okay. So actually, we can also consider open question that I still have. Is the Dehn twist trivial after the stabilization by S2 cross S2? Okay, I will stop here. Thank you.
I think Dave's internet went out, so I'll open it up for questions.
Maybe I could ask a question. So, first off, really nice, Hashan. Are there other manifolds that you know that where this kind of method might work?
Um, actually, I don't know, but I think
Yeah, I don't know either. I just was, thinking about it. But
if we want to consider the non-simply connected manifolds, then I think the only way that can simplify the equivalent stable homotopy class to a non-equivalent stable homotopy class is to consider the quotient invariant. But I don't know any similar result which for full manifold which has this the structure of index bundle as this one. So right, so the essential part of the proof is to replace the condition on the signature by the condition on the index bundle. So, and I think for any full manifold, the only possible non-trivial Chern class of the index bundle is the second Chern class. So I expect that for other full manifolds, we will have some non-trivial structure of the index bundle, but I don't know. Sorry.
Okay, thanks.
Do you mind if I ask a question?
Yeah.
Yeah, I guess, could you say a little bit more about the proof that the S1 equivariant thing detects it?
S1 equivalent, so
or is non-zero? Yeah, like, is it basically from that model example with S3 and CP2? Is that the idea?
yeah. So let's see. Okay, so previously for the non-equivalent one, we have a non-trivial hop element from the 13th cell to some 9 cells, and which is an obstruction to find the non-trivial map from the 13th cell to the 10th cell in the target. However, if we consider the equivariant invariant, then let me use another color. So if we consider the equivariant S1 equivalent invariant, then the dimension of cells in the domain can be reduced to 8, 9, 10, 11, 12. So we see that in the example here, we can apply the equivalent Hopf theorem to reduce the dimension of the domain. So we just do the same thing for this complicated case. And the dimension of cells in the target is unchanged because the S1 action on target, as in this example, is trivial. So, but in the theorem, it will be more complicated. Actually, we have to first move this edge to the left-hand side. So we move SH to the domain, and it becomes S negative edge. We are able to do this in the stable homotopy category. So after we do that, the S1 action on the target would be trivial. So if we apply the equivalent Hopf theorem, we only we only reduce the dimension of the cells in the domain, and we don't change the dimension of cells in the target. So we still have 0 cell and 10 cell. And now, although we have a non-trivial map from 12 cell to the 8 cell, which is new, but we can prove that other attached maps are trivially. Other attached maps are stably trivial. So we are able to find the non-trivial map from the 12 cell to the 10 cell, which is still eta times eta, and it's non-zero. So does it make sense?
Yeah, I think so. I could also just look at your paper, but I appreciate you spelling that out. Thank you.